Hello everyone, I'm Bazan Yusuf from the University of Leeds, United Kingdom. Today's talk is going to be about energy efficient distributed machine learning in cloud fog networks. We start by giving you the outline. So we're going to introduce a number of subjects that are very important in the paper. And then we're going to talk about briefly a number of real-world applications of artificial intelligence and machine learning. We're then going to motivate the work and then define the problem statement, followed by the evaluated network architecture. And then we're going to list a number of key assumptions that are very important in the formulation of the problem. And then finally, we're going to talk about the input data, followed by detailed discussion on the results, and any final remarks will be given at the end of the presentation. There are 5 key subjects in this paper: IoT, fog computing, artificial intelligence or machine learning, cloud data centers, and virtualization. The first two, IoT and fog computing or distributed processing. In Internet of Things or IoT, billions of everyday objects are expected to be connected to the internet. Normally, IoT devices are equipped with multiple sensors to collect data about the physical world. This leads to the generation of big data. Machine learning models rely heavily on data for training purposes. Hence, IoT makes a ripe environment for this purpose. Fog is a distributed processing concept which extends the cloud functionalities to the edge of the network. This was introduced by Cisco back in 2012. Now, any device can be a fog node if it supports processing, data storage, and networking. Some examples of fog nodes can include switches, gateways, access points, and surveillance cameras. In terms of the number of nodes, on the IoT layer, most number of nodes are expected, then followed by the fog, and then the data centers. Now, modern artificial intelligence or AI tools provide unmatchable performance in many applications such as image and natural language processing, speech recognition, and robotics, to name a few. Machine learning is a subset of artificial intelligence, and deep neural network specifically is one of the machine learning tools. DNNs are widely used by mobile and IoT services. The next two subjects are cloud data centers and virtualization. Cloud data centers comprise of thousands of high-end servers that are used to provide services remotely over the internet in the form of different models such as infrastructure as a service, or IaaS for short, software as a service, platform as a service. And finally, virtualization is a key technology which allows the decoupling of hardware from software. Hence, device heterogeneity at the IoT and fog layers can be hidden in this context. Real-world applications. We have, for example, traffic monitoring and prediction, traffic management and control, autonomous cars. There are so many real-world examples. However, we've only chosen a few to put things into context. In traffic monitoring and prediction, GPS data, for example, is used and analyzed to predict traffic levels in future. Video data from traffic lights from CCTV cameras are used in real time to detect traffic anomalies such as runway drivers, queues, and etc. And then data from vehicle cameras, all types of sensors on board the vehicle are used to decide what actions to take by the vehicle independent from the intervention of humans. Now, what motivates the work in this paper is that in contemporary times we have faster and more powerful central processing units in IoT devices. As a result, these devices are able to process complex machine learning functions to some extent on individual basis and to a larger extent on collective basis. IoT devices are equipped with different types of sensors for data collection. Hence, the scope for data generation will increase for artificial intelligence or machine learning based applications. Now, traditionally, due to the processing intensity of artificial intelligence or machine learning applications, the centralized cloud data center has been an attractive proposition. However, offloading all types of tasks to the cloud leads to added overheads due to communication. Hence, a cloud fog architecture extends the services of the cloud closer to the source of the data, in this case the IoT devices. This way, simpler processing tasks can be hosted by the IoT devices, and the more intensive tasks can be offloaded to the cloud. Defining the problem statement. Modern machine learning, mobile and or IoT applications such as natural language processing and driverless cars or autonomous cars demand lots of computational power. This computational power is applied on large amounts of sensor data. On the other hand, these applications impose stringent constraints on performance metrics such as latency, reliability, and power consumption. These challenges have compelled network architects to evolve from the traditional centralized cloud processing towards a more distributed one, such as a cloud fog network. In a cloud fog network, the level of device heterogeneity is very high. For example, fog devices can be manufactured by different vendors, as well as being geographically distributed all over the network. Considering these challenges, we aim to optimally place artificial intelligence or machine learning tasks in the cloud fog architecture so that the total power consumption that comprises of networking and processing is minimized. Right, so the evaluated network architecture. So we have a cloud fog network architecture that comprises of 4 main layers. The bottommost layer is the edge network, followed by the access network, the metro network, and then the core network. In this work, we've used a passive optical network to aggregate the traffic from the IoT devices towards the upper layers. A passive optical network, or PON for short, is very attractive due to its high scalability, cost effectiveness, and energy efficiency. And then we have the cloud data center that is accessed via the core network. The core network uses an IP over WDM technology. In this work, we have 4 main layers of processing. From the bottom of the architecture, we have processing that can be that can take place at the IoT layer, and then we have processing that can take place at the aggregation point of the access network. We refer to this node, this processing node, as access fog. We have 3 of them in this work. We're going to go over it in more detail in the results section. And then we have another level of fog, which we refer to as metro fog. And finally, we have the cloud data center. On the left-hand side of this architecture, we have a virtualized machine learning task, or a deep neural network specifically. So a DNN model, we've virtualized it into a set of interconnected virtual machines. As can be seen, each layer comprises of a number of neurons, and then we have on top of this another layer which we refer to as abstraction layer. Each layer is encapsulated into a virtual machine, and then between the virtual machines we have virtual links. These links are used for communication purposes and synchronization between the different virtual machines. And then we have different IoT nodes that we have multiple IoT nodes that stream their collected data into the input layer of the deep neural network. Right, so what are the key assumptions in this work? The CFN architecture, or the cloud fog network architecture, is assumed to be fully virtualized. What this means is that, as mentioned previously, the deep neural network layers are abstracted as or encapsulated into virtual machines interconnected by virtual links, as shown in this figure. So the advantage of virtualization in this case, the IoT or the fog layers can be abstracted to hide device heterogeneity across multiple processing layers. So in this case, we have different DNN tasks that can be created, destroyed, and migrated on the fly. Also, in the DNN layer or input layer, we assume that different IoT devices are connected to this layer, and therefore we have different virtual machines that act as input virtual machines, and these virtual machines are allowed to be only placed onto the IoT layer. Then we have the deep neural network. The deep neural network is a task. In this work, generally, deep neural networks require two phases. The first phase is training, and the second phase is inference. In this work, we've assumed the latter because of simplicity. Training is a very difficult job that can only be done by high-end servers. Mostly, this is done in very powerful computers located in the cloud. Right, so the problem is formulated as a mixed integer linear programming, MILP. It is mixed integer because we have discrete and continuous variables in our model. The cloud fog architecture is represented by a number of sets, parameters, and decision variables. We have all of them shown here on this slide. We're not going to go through all of them as they are too many. For more details, the paper can be, we've provided a lot of information in the paper. So also through various linear cost functions, the overall power consumption is minimized, subject to various constraints that I am going to talk about a little bit more in the upcoming slides. So the power consumption, as mentioned before, comprises of two parts: network power consumption and processing power consumption. So the network power consumption is calculated through this equation here. We have a PUE factor of networking equipment multiplied by a proportional power consumption of that equipment plus the idle power of that equipment. These terms are going to be talked about more in the upcoming slides. The same thing is applied to processing power consumption. And then the objective is to minimize the sum of the networking and processing power consumption, subject to a number of constraints. The first one, we must ensure that all virtual machines are embedded. And then the second one, virtual machines that are input input virtual machines, they must be only allocated to the IoT layer because the data only comes from the IoT layer. And then we have the flow conservation constraint that conserves the traffic flow in the network. The remaining constraints we've omitted on this slide, they are basically binary indicators. We use these to add the idle powers of different devices. We have capacity constraints on both processing and networking devices. And then we have constraints to make sure that physical links between virtual machines that are virtually connected are also established in a task. Right, so the input model, the input data and the results. These two tables show the input data for the processing equipment and the networking equipment respectively. So the processing devices are representative of, are chosen based on a representative, they are representative devices of IoT, access fog, metro fog, and cloud data center. So going back to the architecture, the processing capability or the capacity of these devices increase as you go up the network hierarchy. So the IoT device, for example, we've assumed a Raspberry Pi Model 4 with 4 GB of storage, a maximum power consumption of 7.3 watts, 2.56 watts for idle power consumption, and then we have the capacity in gigaflops and its efficiency in watts per gigaflops. In this work, as shown in the bottom figure, we have used a linear power profile with an idle and a proportional part. So the idle, the red vertical line, is the idle section of the power profile. So as soon as a networking or processing node is accessed, this much power is consumed, and then beyond this we have a proportional section which is dependent on lambda. So lambda can be the workload. Also, in this work we've assumed that for high capacity networking equipment such as metro switches or routers, core switches or routers, only 3% of the idle power consumption is associated to our application. This is because these equipment are used by thousands of services and users. So it is only fair to attribute a portion of the idle power consumption to our application. In total, we've assumed that we have 30 IoT devices in the network. These are randomly distributed among 10 zones, with each zone being connected to a access point, in this case an optical networking unit. Each zone comprises of 3 IoT devices that are connected via wireless or Wi-Fi links. In this case, the optical networking units are distributed among 3 aggregation points, such as the OLT devices, and this is done randomly with groups of 3 or 4 of them connected to a single OLT device. The number of virtual machines in a DNN task is randomly distributed between 2 to 4, and then processing demand per non-input VMs is randomly distributed between 2 to 13.5 gigaflops, and then between 0.01 to 0.1 gigaflops for input virtual machines. Then the traffic is also randomly distributed between 1 to 4 megabits per second and 0.01 to 0.05 megabits per second for input virtual machines. And where applicable, we've assumed a power usage effectiveness factor. This is to account for cooling overhead at these nodes. So the cloud data center has the best PUE of 1.1, and then we have the core node which has a higher PUE, followed by the access fog and the metro fog that have a PUE between 1.1 to 1.25. Now, discussing the results, figure 2 at the top here shows the total power consumption on the y-axis versus the number of tasks on the x-axis. These tasks we refer to as virtual service requests. And then we have the power consumption for the baseline approach compared to the power consumption of the proposed approach. The baseline approach is when the tasks are offloaded to the cloud, and the proposed approach is when the MILP model is used to allocate the tasks in the cloud fog architecture. And then we have two scenarios for each approach. Scenario number one, when the tasks have only a single input. And then scenario number two is when the tasks have, each task has 10 inputs, i.e. 10 different IoT nodes stream their collected sensory data to the DNN models. As we can see, during low workloads from 1 to 9 with the proposed approach and a single IoT input, significant power savings can be obtained compared to the baseline approach for the same scenario. These savings were 33%, a maximum of 33%, and in the worst case scenario, this dropped down to 27%, which is still significant. The worst case scenario here we mean is when the tasks are allocated to more powerful fog or cloud servers in the architecture. The best case scenario is when all the tasks are allocated to the IoT layer, because the IoT nodes are low power devices. And then these two figures show the breakdown of the processing versus the apologies. These figures show the distribution of the workloads in the cloud fog architecture with the proposed approach. So in the scenario where we have a single input, during the low workloads, we can see majority of the tasks are allocated to the IoT layer. And then when the IoT layer becomes full, we utilize the cloud data center in combination with the IoT, some of the nodes in the IoT layer. This is to avoid activating additional servers in the cloud. And then in the case where we have 10 IoT inputs, we can see that the utilization of the IoT layer increases. This is because since the input nodes are distributed in the network, it makes more sense to offload tasks to neighboring IoT zones instead of going straight to the cloud data center. In fact, the cloud data center is the most effective location for processing, but in this case, the model prefers to allocate as much workload as possible to the IoT and then go to the cloud or the access fog in a very limited scenario. So what is interested here is that the access fog and the metro fog have never been used in this case. This is due to the fact that the access fog and the metro fog have very inefficient processing servers compared to the IoT and the cloud data center, although they are very close to the IoT devices compared to the cloud data center, where we have to access it through the core network. And then this set of results, basically we show a breakdown of the total power consumption into networking and processing for both scenarios with the proposed approach. So in scenario number one, we can see the networking power consumption is slightly less than scenario two, because scenario two, the IoT nodes are distributed in the network. and then the processing power consumption in the proposed solution is comparable in both cases. And then the next set of results, as we mentioned in the previous slides, that the access fog and the metro fog were almost not used at all. We basically, with this figure, we are trying to corroborate the claims we made that the access fog and the metro fog have very inefficient service, and this is the only reason why the model never chooses to utilize them. So we've run the results again, but this time we're assuming that a cloud data center does not exist. So the tasks can only be allocated between the IoT and the two layers of the fog, the access fog and the metro fog. So with the single inputs, the green curves show that when we have a data center, the power consumption after the 12th request is much less than the case where we don't have a cloud data center. This is because the tasks have been allocated to the access fog and the metro fogs. And then we've done the same thing for the case where 10 requests, where 10 input, where we have 10 input IoT nodes in the requests, and we can observe the same trend that we did with the first scenario. With the data center, we managed to obtain a lot of savings due to its efficiency in processing, and without a data center, this is not possible. Okay, so concluding and future works. So we have introduced a flexible optimization framework which allows for generic machine learning models to be abstracted as virtual service embedding problem in a cloud fog network architecture that comprises of heterogeneous layers of processing. We've studied the impact of user distribution on the performance of the proposed approach compared to the savings of the legacy cloud data center. The results showed that significant power savings can be obtained through the optimal combination of IoT and cloud data center layers. We have observed that high-capacity fog servers located deeper in the network were bypassed in favor of the highly energy-efficient cloud data center. Future work can include the development of a heuristic algorithm of improved computational complexity. The current model is very complex to run. We are planning to study realistic core network topology such as the AT&T network, BT network, or the NSFnet. And then we are going to look at deploying energy inefficient cloud data centers and study its impact. And then we're going to look at quantifying the amount of traffic exchange between different layers and study its implications. And then last but not least, looking at different renewable sources at fog sites. Thank you so much, and I'll be pleased to answer any questions you may have.